Good day and welcome to the Moscow Telecommunication Seminar. Our today's speaker is Nikolay Korolev. Nikolay Korolev has received his bachelor and master's degree in applied mathematics and physics from Moscow Institute of Physics and Technology in 2016 and 2018 respectively. Currently, he is a PhD student under the supervision of Evgeny Khorov at the Moscow Institute of Physics and Technology. And also he is a researcher at Huawei Moscow Research Center. Today he will tell us about his research about analytical modeling of Wi-Fi multilink. Nikolay, the floor is yours.
Hello everyone. Well, as already said, I'm going to talk today about an analytical model of multilink operation in saturated heterogeneous Wi-Fi 7 networks. Let me start with the introduction. Why do we consider this topic today? Today, the demand for high throughput for many applications in wireless networks keep growing, and it puts more and more restrictions and targets for throughput and latency on Wi-Fi transmission. So this is a quite challenging topic, and in order to improve throughput and decrease latency, to address this challenge, a new standard amendment, namely IEEE 802.11b, has been initiated and now is under development. Well, it introduces some improvements for throughput increase, such as higher MCS, for example, and higher bandwidth, which can be used for the transmission. But maybe the most prominent feature of the upcoming amendment is multilink operation. So let me give you a few words about multilink operation and some challenges which it faces right now. The multilink operation is a feature of BE standard, which allows to perform a transmission via two links, via two channels simultaneously. Well, actually, we can use more than two links, but well, in our research, we are now considering two link devices, and it is expected that the first devices which support multilink operation will support two links for the transmission. Using multilink operation, multilink feature, we can transmit, we can send a single data flow using different channels, which can be located even like in different bands. For example, here you can see that link 1 belongs to 2.4 gigahertz band, and link 2 belongs to 5 gigahertz band. They can also have different bandwidth. Multilink operation provides quite flexible and promising tool for throughput increase and latency decrease. Well, the multilink operation can be divided into several cases. Well, the first categorization, which can be said, is about simultaneous transmission and reception and non-simultaneous transmission and reception. Well, by default, multi-link operation uses simultaneous transmission and reception, which means that the transmission at different links can be performed independently, and we have no problems while transmitting at one link and receiving some frames at another one. But in some cases, for example, when the spectral distance between the channels used by different links is low, then we might encounter cross-link interference. That is when the transmission on one link can impair the reception at another link, which is illustrated here. And well, in this case, the performance of the transmission, the throughput, will be decreased. So, in order to cope with this problem, with this issue, new channel access schemes are needed for proper transmission in order not to waste channel resources. So, and this is a big question: how to design channel access schemes. And our research in general aims at analyzing such channel access schemes, telling which of them are better in which cases, and so on. So today we will mostly talk about an analytical model for some of the basic schemes, which can give us some insight about non-STR operation. Well, let me explain you well, the considered schemes. We consider two schemes which were originally discussed in task group of .11b standard, and both of them, actually all of the schemes which are now under discussion, they use EDCA, standard EDCA procedure as a basement. And the first scheme which we consider is called no waiting scheme, and let me explain it in more details. Here in our research, we usually suppose that the client devices are non-STR, are working in non-STR mode, and the access point is working in STR mode. Well, because the access point is usually it usually has much bigger size, and it can contain more complex and expensive chips. So here we consider the transmission initiated by a client device which is operating in NSTR mode. And well, the device has a separate station for each link. We call these stations affiliated with the MLD, with the multi-link device, and each of them performs EDCA procedure in the corresponding channels. But we need to synchronize these procedures in order to avoid the situation when we transmit in one link and we receive some frame in another link. Generally, what we need to do in order to avoid such situation is to align the ends of the transmitting frames. And the first scheme allows us, ensures that we don't fall into such situation, and it works as following. Let us consider, the situation when the affiliated stations to both links are counting back off, so both channels are idle, and at some point one of the back off counters reaches 0 value, and at this point we can start the transmission in this link. But at the same time, here we see that at the second link the back off counter is not 0 yet. Its value is free. So in the first scheme, we initiate the transmission at the first link, and we don't wait for the other one. So when we start the transmission on the first link, we say that the second channel is now busy due to cross-link interference, and we actually don't know what happens in this channel. We just consider it as busy. Then, here in this case we perform a successful transmission, and at the same time in the second link there is an ongoing alien transmission from some other station. So that is why the busy period here in the second link can be much longer than the duration of our successful transmission in the first link. Yeah. So when after the successful transmission, when we start to count back off once again in the first link, it can happen that the second link is it is busy and we just working only in one channel. In this example we lose the contention in the first link, so the channel becomes busy, and we continue to contend for the channel in the second link. So overall, in the first scheme which we consider, if any of the back off counters reach 0 value, we immediately initiate a transmission in the corresponding link, and we do not wait for any other link in order to perform simultaneous transmission. Let's talk a bit about the waiting scheme. In the waiting scheme, we usually we actually try to perform joint transmissions. That is the transmission in both links in the same period of time. So here, unlike in the previous case, we don't start an immediate transmission in the first link, but we try to wait for the second link to start the joint transmission. So in order to do this, we freeze the back off counter at 0 value until another back off counter reaches 0 value, and only after both back off counters reach 0 value we initiate the joint transmission. Notably, we need to make sure that the ends of the transmissions are aligned. This is done, as I said before, in order to prevent the situation of simultaneous transmission in one link and reception in another one. So here the duration of the data frames in both links are equal to each other. And the next contention period in both links, the starts are the same. Here is one good remark. What happens if we lose contention in some link during waiting for another link? Well, in the right part of the slide, we see that this is exactly this situation. In the second link, the backoff counter reaches 0 value at some point and freezes it at 0 value in order to wait for another backoff counter for another link in hope of the joint transmission. But the first link becomes busy, and according to the current draft of the BS standard, we need to restart the backoff counter. So we change it from 0 to a new value. It can be explained by the following fact. If there are several, if we don't restart this value and just start an immediate transmission after we sensed another channel busy, then we will fall into collision with high probability, because there might be several non-STR MOD devices, and there might be several devices which froze their backoff counters at 0 value, and if they sense the first channel as busy at the same time and start the transmission at the same time, they will fall into collision. So that is the reason why we need to restart the backoff. So these two schemes, which I just shortly described, were discussed in the task group, and now are compatible with the current draft of the standard. So let us discuss what do we want from the developed model. We want to build an analytical model for these schemes. In the following scenario, we consider a simple scenario with no hidden stations. Each station can listen to any other station's transmission. Each station has saturated traffic in the uplink direction. And in our scenario, we characterize each of them by a tuple N1, N2, N3, which correspond to the number of legacy devices in the first link, legacy devices in the second link, and the total number of multi-link non-STR devices which operate in both links. What is new in this model? Well, the existing works related to analytical modeling of non-STR operation usually suppose that there are no legacy stations in the network. They usually say that all the transmissions are joined, and it means basically that in some sense, both channels are kind of synchronized. However, if there is at least one legacy station in any of the channels, then channels become asynchronized. That is the situation when the virtual slots in both links are not aligned, for example, one virtual slot in one link can contain several virtual slots in another link. Well, and this developed model is the first one which takes into account such phenomena, the presence of legacy stations. And next thing I want to say that this model, it turned out that this model is basically suitable for both schemes which I described before. That is because of the saturated traffic for all the stations and in both links. It means that we will have asynchronous behavior in different channels, so they wouldn't be synchronized in most of the time. That is why the number of joint transmissions for the waiting scheme is very, very low, and therefore both schemes are very similar in performance. Okay, so next thing I want to say is the main insight about the developed model, the main idea of the model. So, as we previously noted, when an MLD transmits in one link, it cannot sense the channel corresponding to the other link. That means it cannot contend for the channel access in the last link. So the main insight of our model is that it can be considered as Bianchi's model with lowered number of contending stations, because some MLDs can transmit in one link and they don't participate in contention in another link. But other things during the contention period are the same as in the standard case, which is considered in Bianchi's model. Okay, now I will start to explain the model in more details. Let us start with some definitions. The first definition we introduce is Rn, which is it is the total throughput of a saturated network of n legacy stations obtained from Bianchi's model. Given that we fix all other parameters such as MCS used, bandwidth, frame duration distribution, and other parameters. Here we introduce the assumption that the probability of successful transmission during contention doesn't depend on the type of the contending device, whether it is a legacy one or an MLD one. So under such assumption, we can say that the total throughput of all X legacy devices which contend with Y MLDs in channel I, in our case I can be 1 or 2, it equals just X over X plus Y multiplied by R X plus Y. Let's move on. And here we introduce one of the main probabilities. We say, okay, we say let Sij be the probability that at random time instance in channel I, we fall into a virtual slot with J transmitting MODs. Firstly, we randomly select time instance, we fall into some virtual slot, and we just look how many MODs transmit in this slot. If it is 1, then this virtual slot is a successful virtual slot with 1 transmitting MOD. If J, the number of transmitting MODs, is higher than 1, then it is a collisional virtual slot. Yeah, but by the way, if J equals 1, it doesn't mean that it is a necessary successful slot. There might be other legacy stations which transmit in this slot. So anyway, I think I brought you some insight about this probability. Well, and here we state that the throughput of each legacy and MOD station in channel I equals well, the following. Let me try to give you some idea about these equations. The idea is that at any like random time instance, we want to know how many MODs are transmitting now in the other link. This is the crucial information because it depends on how many stations are contending in our channel. For example, in channel I, well, the number of contending stations directly depends on the number of transmitting MODs in another channel. So that is why in both equations you see I overline, because like I overline means the index, an index of another link. If I equals 1, then I overline is 2, and vice versa. Yeah, and well, we just well, in the first equation we just well, if J MODs transmit in another link, then the expected throughput in this virtual slot is calculated with the total number of contending stations less than J. So we just subtract J from the total number of contending stations, and then we just take the expected value of this expected throughput, expected value over the number of MODs contending in channel I. Okay, but well, here is the question. We need to know how to calculate Sij probabilities. We need to calculate them somehow, and in order to do this, we introduce P probabilities, Pixy, which has the following meaning. This probability is the probability of the fact that X legacy devices and Y MODs transmit in a random virtual slot in channel I. When we introduced Sij probabilities, we said that we take At first, we take random time instance. Here, we say we take a random virtual slot. And that is, these are actually a bit, different things, because virtual slots have different durations. So, we need to be quite accurate with it and point out some differences between them. Okay, here next we introduce the average duration of a virtual slot in channel I. Actually, as we do it in Bianchi's model. And so actually the formula is a bit, it is quite similar, but the probabilities calculation before t values, this calculation is different in our case. Here we introduced TE, TS, and TCN. The average duration of virtual slots of empty, successful, and collision slots with end transmissions there. Okay, now we have two unknown probabilities, two sets of unknown probabilities, S probabilities and P probabilities. And now we will write out some equations which include both of them, and that will allow us to calculate all of them. So the first set of equations, which includes both S and P probabilities, is following. We say that let's take the probability, the definition of S probability. Well, because we take a random instance in channel I, then we say that in channel I, 0 MLDs transmit in channel I. In several cases, if a virtual slot is empty, if the virtual slot is successful, and one legacy station transmits, or it is collisional with two or more legacy stations in collision. And we can write out similar equations related to different number of transmitting MLDs. In the last line, we have only collisional slots in consideration, because in this case J is more than 1, so it means that at least 2 MLDs are transmitting, and it means that this virtual slot is collisional. Okay, we need to introduce one more probability, which is actually obtained from the Bianchi's model. We say that we have n legacy stations in channel I, k stations affiliated to MLDs containing in channel I, and we say that we introduce the probability. The probability of X legacy stations containing in a random slot Y MODs containing in this slot, well, trying to transmit, not contending, trying to transmit, under condition that n legacy stations participate in contention period, and k MODs participate in contention. So and I is the index of the channel. So this value can be obtained directly from the Bianchi's model and equals this. It is quite easy equation which can be derived from combinatorial ideas. Okay, and actually the last set of equations which we need in order to calculate all previously introduced probabilities is the following. We say that we consider the definition of P probabilities, which is the probability that in a random virtual slot, X legacy stations transmit and Y MOD stations affiliated with MODs also transmit. Okay, we consider, let me explain the idea of this equation. Here, once again, when we consider a given virtual slot, random virtual slot, at the beginning, when the transmission starts, there is a contention period before. In the other link, we still see, in the other link, it's still a random time instance. So that is why we see S probabilities in the right side. So in order to understand what is the probability of transmitting X legacy stations and Y stations affiliated with MODs, we need to know how many stations participate in contention period, right? But that thing depends on the number of MODs transmitting in another link. So, the S probability corresponds to the probability to the probability of J transmitting MODs in another link, and the second term corresponds to the probability of X transmitting legacy stations and Y MOD stations itself, given the number of contending stations. So that is the general idea. And it turns out that this set of equations, together with previously introduced equations, all of this is enough for the calculation of P and S probabilities. And we can obtain them numerically, and then put these values into the equations for average virtual slot transmission, and finally in the first equation related to the total throughput of legacy and MOD stations corresponding to channel I. Finally, to get the total throughput of all MLDs or all legacy stations, we need to just sum up the obtained values over different channels. Well, that's it. This is a short explanation of the formulas of the model. And let me show you a couple of results about accuracy and other things. Well, the first thing is following. Well, before developing the model, one obvious question appeared. The question is following: can we just use Bianchi's model? Can we just say that, okay, an MOD has two affiliated stations, and well, we would consider each station in each link just as a separate device, just a separate station, same as legacy station. Well, calculate the throughput of each individual station separately in different channels, and then just sum up values, the obtained values over different channels. Well, it is what I just said is actually about. It is very similar. It is about very similar to STR operation, when we don't have such restriction that transmitting in one link prevents reception in another one. So, in some cases, it turned out that in some cases the discrepancy in the results, in the predictions and simulation results is quite huge. For example, here we see that in the case of in the configuration of 111, which corresponds to one legacy station in the first link, one legacy station in the second link, and one MLD operating in both links, the difference between Bianchi's model and the real simulation result is up to 50%. Well, this is well, quite huge, and we needed to develop a new model. So we see here that the developed model is quite accurate, and the Bianchi's model actually overestimates MODs, because, well, it considers MODs as working in STR mode. But NSTR mode, well, it has some restrictions, so the throughput of STR devices, NSTR capable devices is lower than STR capable devices. In our work, we also considered well, fairness issue, and let me tell you a couple of words about this. Well, in order to measure some fairness, we used Jane's index. Our formula is written here. The value of Jane's index varies from 1 divided by n to 1. 1 corresponds to the ideal situation when all the values of all the arguments are well, equal to each other, and 1 divided by n is like the worst case when we have the highest fairness issue. So in this scenario, which we considered the symmetric scenario with one legacy stations in both links and changing number of MODs, the fairness is lowest in the case of 111. And let me also say a few words. How do we measure Jane's index here? Because we have two channels. Here we calculate Jane's index separately by channels. So, for example, we get channel 1, and we consider all the stations affiliated to channel 1 and their throughput. And we put these throughput values into the formula for Jane's index. And that's it. So in general, we consider two Jane indices for the first channel and for the second channel. In this scenario, in the symmetric scenario, the situation is symmetric, and that's why we see here only one line. Okay, in the case, in the rightmost case with 118, we have almost ideal situation in terms of fairness. It means that, well, in each channel, each station takes almost the same amount of resources. But in the case of 111, we see that the throughput of the MOD is the same as of legacy stations. So it means that the station affiliated with the MOD in, for example, channel 1 gets twice lower throughput than the station than the legacy station in the same channel. So that is why we see here lower number, lowered Jane's index. Let me also give you more examples with different scenario. We also considered this a scenario with 0 legacy stations in the first channel. Well, here what is notable that the throughput of legacy stations is almost the same for all the points except the leftmost one. Well, that is because actually, even though we change, we add one. If we go from the left to the right, we add one MOD, and we remove one legacy station in channel 2, but the total number of stations in channel 2 is the same. And because the channel 1 it doesn't contain any legacy stations, well, the number of contending stations in channel 2 is almost the same. So we don't see any difference in legacy stations throughput. Also, well, we see a quite high peak at point 0.071. Well, that is clear because in this case, the MOD just occupies the first channel fully and has a very high throughput. And the 7 other legacy stations just participate in, just occupy the other channel and and have much lower throughput. Yeah, and that is why the fairness measure, the Jane's index, is the lowest for this point. In the next scenario, we fix the number of legacy stations equal to 2 in the first channel, and fix the total number of devices in our network. Well, qualitatively, the results for MLDs are quite simple, quite similar to the previous results, but the peak at the point 251 is much lower than in the previous case. That is because in the previous case, the whole channel, the channel one was fully occupied by the MLD. Here it is not like this. We have two legacy stations there too, so we don't see so much a difference between legacy and MLD stations. And also because of the generally we have more stations in the network, so we have more fairness. We have higher Jane's index values in general. You see that, well, it is almost 1 for all the cases. Yeah, for the lowest values here, it is still 0.98. So this is generally all I wanted to say specifically about the analytical model, and I would like to tell you a bit about other work which is related to this one. Well, there is an ongoing work about other channel access schemes. We try to understand which of them are better, well, in terms of throughput, and we also take into account the fairness issues. So here are some examples of another schemes, but well, they are not compatible with the standard. They don't follow the standard, actually. The two schemes which we discussed today before, they follow the standard. The rest schemes, they don't, but, well, of course, they are of interest, and we also would like to research them. And okay, the first one is the following. The difference is that we have only one backoff counter. We have the joint backoff counter, which decrements only when both channels are empty, are idle. Yeah, and well, it happens rarely, especially in the asynchronous situation. Yeah, when some legacy stations are presented in the network, and well, our results show that, well, this scheme is not very effective. It's like if we have at least one legacy stations, well, its performance is quite bad. Another scheme is kind of opposite. It is about the following, that that if at least one backoff counter reaches 0 value, it can start a joint transmission with another links, with another stations in several links, if the corresponding channels are idle for some predefined period of time, like PCF interframe space. So well, this scheme is quite aggressive. It actually shows well, good performance in under some conditions, but because of its aggressiveness, it is quite unfair, and this is why we cannot say that this is a good option. Yeah. The last scheme I wanted to mention is channel bonding-like scheme. In this scheme, we distinguish one link and call it a primary link. All other links are called secondary links, and we perform EDCA procedure. We decrement our backoff counter only in this link, and we can initiate joint transmission when this when firstly the backoff counter reaches 0 value, and well, a secondary channel, a secondary link, well, its channel is idle for some predefined period of time. Yes, and well, the last modification of some of these schemes I would like to mention is frame alignment. Well, frame alignment is a mechanism which can be used to increase the number of joint transmissions. Yeah, and the idea is that if we perform well, if we have more opportunities for joint transmissions, if we perform more joint transmission, therefore we have more joint transmissions because we use more links, yeah, for simultaneous transmission, then we will have increased throughput. Well, this the frame alignment idea is the following: is that for example, here in this picture we see that in the first channel, in the first link, there is an ongoing alien transmission, which we listen to, and we extract the transmission duration from preamble, or we can do it after decoding RTS or CTS frames, and look at the duration ID field, and then calculate calculate the start of the next contention period. So after we know the end of the ongoing alien transmission in one link, we can adjust the length of our transmission in another link in order to align their ends, as shown here. After our transmission, in this case, we can have like synchronized kind of synchronized channels. We can have overlapping contention periods, and there is a chance that we will be able to perform a joint transmission after this. Well, this is the mechanism, and well, at first it sounds quite quite promising. But it turns out that, well, it depends on the scheme. It depends on the scenario, and well, in some cases, for example, for the weighting scheme, well, frame alignment actually decreases the performance of MLD devices, of MLDs, yeah. And contrary, for this scheme from the previous slide, with the aggressive scheme, in this case, well, by applying frame alignment, we can tremendously increase the throughput and degrade fairness. So it is a kind of a question when it makes sense to apply this mechanism, and in general, it is actually still a big question. Which scheme can be used in real devices, which provides significant performance increase in comparison with legacy devices, and at the same time, well, provides good fairness. Yeah, and we see that well, the no weighting scheme, it provides some good throughput increase. It is quite fair, but still there is more space for improvement. So, and that is, well, in general, an open question how to improve the existing schemes further. So, thank you for your attention. If you have any questions, please ask me, and we can discuss them.
Thank you, Nikolay, for your interesting presentations. We have several questions in the chat. I will read it for you. So the first question is from Artem Krasilov. In the introduction, you said that in the case of simultaneous transmission, packet durations are the same, and thus their sizes in bytes are the same. That is not true for channels with different MCSs and bandwidths. Do you use such assumptions in your model?
No, I said about maybe if I said it, it was a mistake. I meant that they have the same durations. I didn't want to say anything about the size of the payload.
Okay, I think we can go to the next question. The next question is from my side, and the question is, what is the definition of virtual slot in your model? When does it start and end?
Okay, it is the same as in Bianchi's model. We have virtual slots in different channels. We have a set of virtual slots in one channel, and we have a different, totally different set of virtual slots in another channel.
I guess in Bianchi's model, there is no virtual slots of a channel. There are virtual slots of particular stations. So you divide the whole time in your model in some time periods, which you call virtual slots. Okay? So
yeah, in each channel, yes.
Okay, let's consider only single channel. So in channel 1, for example, what defines a start of virtual slot?
Well, as the same as in Bianchi's model, it is defined as the decrement of the back-off counter of to be precise, non-transmitting station. Yeah.
Okay, but in Bianchi model, you have n stations and all are identical, and they all decrement their back-off counters simultaneously. But in your case, you have legacy stations and you have MLD stations, and due to transmissions in other link, they may decrement not simultaneously. So please, I did not catch the definition of virtual slot in your.
In this case, I could say like if some stations decrement their back-off counter, yeah, and some MLDs don't because they transmit in another link. We just don't take this station affiliated with MLD in the definition of a virtual slot in another channel. So from the formal way, it is okay. Anyway, it's still, you see that in this channel, an empty slot is an empty slot for all stations. Just some stations can decrement their back-off account, and some of them just don't do it. Yeah, but it's still an empty slot. Maybe I hope I brought you some clarification about this.
So, as I understand, in your model, the virtual slot starts when the legacy stations decrement their counters, and if some MLD do not decrement it, it means that it operates currently in some other channel, and all the devices that are working are contending for the given channel, which means that they are all decrement back-off counters simultaneously.
Yeah, you can say so. Yeah, we need maybe to specify on this more, like when there is no legacy stations in this channel and so on. Yeah, but the general idea, yes, you said it right.
Okay, thank you. So we can go to the next question from Alexander Krotov. Is the duration of successful virtual slot assumed to be constant, or can it be a random variable? In the paper, T sub S is defined as the average duration of the successful slot. Does it mean that the duration itself is random?
Yes, it is random, as in Bianchi's model, and in our paper considered AMPDUs with random discrete uniform number of MPDUs from 50 to 64, each of 1.5 kilobytes of payload.
I have some question additional. If you consider saturated case, why do you consider that the transmissions have different lengths? Because in saturation, it's usually assumed that all stations have a lot of packets in any time.
Okay. Okay, I got your question. So, yes, we consider by the saturated conditions, by the saturated traffic, we mean that at any given moment of time, there is a non-zero number of packets for transmission distributed as I said before. Yeah. Well, as far as I know, in other works, including Bianchi's work, well, they consider this situation too. So it is a usual situation, and also I think it also makes sense to consider, because by considering different durations, yeah, different payload, we avoid some kind of regular behavior which can affect our results. So also from this point of view, it makes sense to consider random payload, as it will provide more stable and realistic results.
Okay, thank you. The next question is from Dmitry Bankov. How does T sub Cn depend on n?
Yeah, okay. As in Bianchi's model, it depends, well, in the following way. In general, like if the higher the n, the longer the longer the collision. Yeah, because well, if we, for example, take two, like we consider two cases. In the first case, for example, we have n equals 2. It means that there are only 2 frames in collision. And in the second case, we can have, let us say, n equals 4. And in this case, we would have 4 frames falling into collision. Yeah, and if their payload is derived, is chosen independently from the same distribution, yeah, the maximal value of each the duration of each individual frame in the second case is obviously higher. So yeah, it depends monotonously, increasing with the increasing n.
Thank you.
The next question is from Kirill Chemrov. What happens if virtual slots in different links are asynchronous?
Virtual slot. Actually, well, they are asynchronous, well, most of the time. So this is actually like the main situation we are considering in our work. When we look at the status of the other channel, we suppose that we choose a random time instance in this channel. So from this point of view, well, we work around such case, well, all the time. If you have more maybe more specific question, I could answer it.
One more question. Do you compare multi-link operation with single-link operation? Because maybe it will be better for MLD devices not to use some MLD access scheme, but just to select some single channel with lower load and use it. And do not try to contend for both channels.
Okay, yes, I understand your question. So in this paper about analytical model, we don't do this thing. But in another work, which is under development, we specifically consider the case of STR operation, which is not the same what you just mentioned, but actually it is kind of two legacy devices in both links, and we just see the sum of the results. And actually, and in how to say, in this work about analytical model, we also see some results for STR operation. Well, in one of the graphs, we saw that pure Bianchi's model prediction is actually the result for the MOD of which works in STR mode. About if we focus particularly on the question of an MOD device, of an MOD which works only in one channel, there are actually two different cases, two different stories. The first story is about the following: we have an opportunity to transmit, to work in two channels, yeah. But for some reason, we choose only one link, and we can change. Maybe it's from time to time, rarely, yeah. It is more. I think it is more. It is more about an algorithm which selects such channel. Up to this point, we didn't try to develop this type of algorithms when we can, listen to both channels, and we don't use them as in these schemes, and we just use one channel and that's it, yeah. But there is another story called multi-link single radio, which is much closer, which is how to say, which is exactly about transmitting only in one link, with no opportunity to transmit, to perform joint transmissions. And in terms of MLSR, multi-link single radio, and in terms of this, we are actually now preparing a paper about this, which includes an algorithm for the selection of the active channel. By the active channel, I mean the channel in which we can perform back-off counting and transmitting some frames and so on. Yes. And the last thing I wanted to mention here is that in MLSR it is one story. In other case of in another case, with different capabilities, physical capability, there might be another situation which how to say, for which we need to develop another algorithms. So we need to be quite accurate about the capabilities, and having these capabilities, we can build some kind of algorithms. And yeah, once again, we already will have some results about this for MLSR.
Okay, thank you. Because I think that just a single link operation is much more simple for implementation, and I guess there is a lot of papers in the literature about, you know, usual Wi-Fi before multi-link, how to select the channel in this case. So it will be nice for proving that multi-link is useful and a powerful tool for these cases, to compare it with some single link operation with smart channel selection. But it's maybe, as you said, it's some further research.
Yeah, you're right.
Thank you. I guess that's all for today. Thank you, Nikolay, for your interesting presentation and interesting discussion. I want to thank also all the people in the chat for interesting questions. So thank you. Goodbye.
Thank you.